Hello, and I'd like to introduce you to my son, Cade. Cade, we're going to talk about math today.
Oh,
So what is your favorite part of math?
subtraction.
Why subtraction?
Because I'm good at it.
And Cade, what would you say is your least favorite part of mathematics?
Problem solving.
Well, Cade, I've got a problem for you to solve. What do you think of when I say vertical asymptotes?
Frogs.
So, ladies and gentlemen, according to Cade, today we'll be dealing with frogs. So now we look at the topic of vertical asymptotes. Note that our objective is to determine the equations of vertical asymptotes of rational functions. When we talk about rational functions, what we need to remember is that we're talking about ratios. And these rational functions contain polynomials in the numerator and the denominator. The most basic of the rational functions that we have is the y equals 1 over x. So remember, just as a general shape that you would have used before, remember that you'll have, in this particular case, a branch in the first quadrant and a branch in the second quadrant. The key thing that we're going to be looking at today is that because you would be dividing by 0 at x equals 0, we have what's called a vertical asymptote. The key thing about a vertical asymptote is that it's a vertical line that the graph will approach but not cross. Notice on either side of this vertical asymptote, the y values go to either positive or negative infinity. Another way to look at this just by a grapher, this is an example of the y equals 1 over x. And notice at the value of x equals 0, it's undefined. And if you can see on here, the grapher doesn't quite do it justice, as it tries to put a line here where it doesn't exist. Now the examples we're going to look at will center around the idea of equations of vertical asymptotes of the rational function. The key thing when we're looking at these particular equations, we're looking at the denominator. And essentially, the question that we ask is, what makes the denominator equal to 0? So if we look at this first example, y equals 3 over x minus 2, we look at the denominator of x minus 2. We set it equal to 0 and solve. So on this one we could do without showing this, but we end up with x is equal to 2. Now, as far as the graph, whatever that graph happens to look like, what we know is that we can put a vertical line, and we do show the equation. It's not 2, it's x equals 2, and the graph is not going to cross that. So whatever the graph happens to look like, it's not going to cross x equals 2. This we'll just label with VA, VA for this vertical asymptote. Back to the grapher, what this would look like would be something like this. So we notice at x equals 2, put this in a different color here, at x equals 2, where the grapher puts that solid line, this would be a dotted line that the graph will not cross. Now, moving on to our next examples. Again, we look at the denominators. So if we look at number 2, our denominator of x plus 1, again, to find the vertical asymptote, we set x plus 1 equal to 0. Now this is something you don't actually have to write because we can see that negative 1 will make this a true statement. So we have x is equal to a negative 1. That again is our, I'll put VA for vertical asymptote. That is the value that makes the denominator equal to 0. Remember from what we've done previously, x equals 3 makes the numerator equal to 0, and that is the root or the x-intercept or the solution. So if we look again at the grapher on this x minus 3 over x plus 1, we get the following. So if we turn on the x minus 3 over x plus 1 and graph it, notice now, since negative 1 is our value that makes the denominator equal to 0, that is our vertical asymptote. On to number 3, we have in the numerator in this case here, we have x times the quantity of x plus 2 over the quantity of x minus 2 times x plus 2. Now, from what we've done with wholes, we can go ahead and divide this part out, and we note that x cannot be equal to a negative 2 because negative 2 is the 0 for those two factors. And so we would be left with x in the numerator, x minus 2 in the denominator. So again, we're looking at x minus 2, and our vertical asymptote, I'll note that with VA, is x is equal to 2. So what that's saying is that's the vertical line the graph will approach and not cross. And we're not so interested in the full graph, we're interested in the vertical asymptote. As an aside, this x being in the numerator, remember that tells you that x equals 0, the x value of 0, is our x-intercept. So that part would be our x-intercept. So if we look at the graph of this one, this is a little more complicated function. So we'll turn off the graph that we just had and put this one on. And if we graph that, notice that x equals 2, that's the value that makes the denominator equal to 0. The parts that we had with the x plus 2, negative 2, there's actually a hole at that specific place right there. But your general graph would look like this. Now we'll put this, when we actually draw them, we'll draw this with a dotted line, because this line right here at x equals 2 is actually not part of the graph. Now moving on to our next part, this is a rational function. And the key thing about a rational function, even though there's 9 minus and then this fraction, the fact that we have this fraction with polynomials in the numerator and denominator tells us we have a rational function. Now, in this particular case, there are 2 of these vertical asymptotes. X is equal to 7, x is equal to negative 3. Remember, vertical asymptotes, I'll just denote that with VA, are the values that make the denominator equal to 0. This is after you've divided out the wholes. So if we were to make a quick just sketch of this, x equals 7, if I said this was the value, x equals 7, negative 3, and I'll just mark that and we'll say that that's negative 3. These are the vertical lines the graph will not cross. They'll approach them, maybe going to positive infinity or negative infinity, but they won't cross them. And again, that's the key idea on the vertical asymptotes. So quick review, whenever we talk about vertical asymptotes, the whole point is that after we divide out the wholes, common factors, the values that make the denominator equal to 0, the x values, the equations with x equal to whatever those values are the vertical asymptotes. Now, we'll move on to our next step, and now we'll talk about, and this is a very close relationship to the vertical asymptotes, the domain. Now, from before, what we've dealt with, the domain are essentially the x values that give you a solution, and we'll look at it in a slightly different way. Now, from what we've done already, if we look at the denominator of x plus 1, we know that x equals negative 1 is the vertical asymptote. So the VA for vertical asymptote. Well, the way that we'll show the domain is essentially the opposite. For the domain, we'll say x cannot be equal to a negative 1. So what the domain is saying, this is the one value of x that doesn't give you an answer, because notice on our graph, x equals negative 1, the vertical asymptote, there's no value, there's no answer to the function when we put in negative 1. Now, this is sort of a quick way and sort of an easier way to write this. Traditionally, what you would put down, this is just another way to put this down, and this is probably the more correct way to put this down. You would put in interval notation. So we'd write from negative infinity to negative 1, notice we're using parentheses, or from negative 1 to a positive infinity. So this part, this second way that I wrote it, this is another way of writing it. We'll accept that x is not equal to negative 1. We'll write that as the domain. But please understand, when you look at the book and a lot of other books, they'll show an interval notation, the domain. But these two things, either saying x is not equal to negative 1, or the interval notation, we take as being the same thing. The same thing can be done on the bottom. Now here it's a little bit different because we would divide out, and this is the x plus 4 saying that x cannot be equal to a negative 4. That's a whole. But then we're left with x plus 5 on the denominator. With x plus 5, that's saying x cannot be equal to a negative 5. And that's how we would write our domain. And essentially what we're saying, those are the only two values, negative 4 and negative 5, that don't give us an answer. Meaning every other value will give us an answer. Now if we wanted the vertical asymptote, the only vertical asymptote on this particular problem is x is equal to a negative 5. Because when the wholes are not vertical asymptotes. We divide those out first, and then with whatever remains, that's how we determine the vertical asymptote. And notice the domain says that we cannot have that value. So in effect, they're the opposites. Now, the last thing that we'll go on to, and you'll see this on your assignment as well, is where you're building a function. So we'll give one example, and there are also some good examples in your book to look at for your assignment. So it says to write a function that fits the following criteria. So now we'll put some things together that we've worked on previously. It says we want a function with a 0 at 2, vertical asymptotes at x equals 1 and x equals 3, and a whole at the ordered pair of 5, 3. So this number 3 will take a little bit more time to understand what that means to find a whole, because remember, a whole is where you have the same factor in the numerator and denominator. We'll start with the 0 at 2. So we'll try to do this with different colors so we can get an idea. So a 0 at 2, if we're going to first make our function, we'll call our function f of x. So we'll say f of x is equal to. Now we'll start with the 0. So a 0 at 2, and we'll use this with green. Maybe. There we go. Okay, so we want a 0 at 2. So what we would do in the numerator is 0. We would write down as x minus 2. Then we'll go on to our next part, where it says vertical asymptotes at x equals 1 and x equals 3. Now remember, those go on the denominator. So we'll go x minus 1, because that means 1 makes the denominator 0, and x minus 3. So in green, we have our 0 at x minus 2. In red, we have our vertical asymptotes, x minus 1 and x minus 3 give us these vertical asymptotes of x equals 1 and x equals 3. Now for the last part, we'll do this one in blue. How do we get a whole at the x value of 5 and the y value of 3? That's an ordered pair, which means when we graph it, we'll have no answer. Well, remember, when we have a whole at 5, x equals 5, that means we'll have x minus 5 in the numerator x minus 5 in the denominator. Our issue is, though, how do we assure that the y value where that whole will be is 3? And here's our process. So the first thing we'll do is actually go backwards. We'll rewrite this here in a second. We divide out our wholes. And what we're going to do is we're going to find the answer to f of 5. So we put in 5. This is when we divided out the whole. So it looks like the following. In the numerator, we'll have 5 minus 2. In the denominator, we'll have 5 minus 1, 5 minus 3. So this will end up with a 3 in the numerator, and 5 minus 1 is 4. 5 minus 3 is 2, which leaves us with 3/8. Now, what this is saying is when we put in 5, we get 3/8. But remember, when we put in 5, we want to get, I'll circle it right here, an answer of 3. So we look at this, and we can see that if we multiply by 3/8 by 8, we get our value of 3. So what that means is we'll take and we'll multiply, and we think of this function, which was, remember, f of x. If we can take this function times 8, that's the same thing as multiplying 8 by our answer, which will divide that out, and it'll leave us with an answer of 3. So 8 times our original f of x is equal to 3. So what that leaves us with is the following equation. So we go back to all of our original. The one we had in green was x minus 2. So we'll have f of x equals, and our numerator will be x minus 2. We'll put parentheses around that. Our denominators, we had, to get the vertical asymptotes, x minus 1, x minus 3, and our whole of x minus 5 and x minus 5, numerator and denominator. And then do not forget, so that we could get our correct answer of the whole at 5/3, we have 8. And that is building a function meeting those criteria. So there's some good examples in the book, and some other examples we'll look at as you work on your assignment.